All right, as I'm assuming all of you can conclude, measuring is going to be important in a science class. We've had 2 labs or activities thus far, and we've measured in both of them. And with every lab activity we have, we're going to do some type of measurement. So we're going to focus on this section talking about those measurement techniques and the units that we use to describe measurements. First, a little story. Let's see, September 23rd, 1999. We got a $125 million Mars climate orbiter that accidentally enters Mars' atmosphere 100 kilometers lower than planned and was destroyed by heat. So the actual orbiter wasn't built to be able to withstand such temperatures at that particular altitude, and it was destroyed. So that's $125 million down the hole. So why did this happen? Well, one of the calculations that the engineers needed to produce and make the vessel required them to calculate a weight. They calculated the weight they used this particular equivalency that 1 pound equals 1 Newton. But that is not true, when in fact 1 pound actually equals 4.45 newtons. So instead of working in the metric system, that's what a Newton is, by the way. When we talk about weight, the metric unit for weight is newtons, not grams. That's the metric unit for mass. And the English unit for weight is obviously, as we know, pounds. So instead of converting over from pounds to newtons, we made the mistake, and so the calculation was wrong. This threw off the orbiter and thus cost $125 million. So this is our cautionary tale to prove that it's important that we get a good grasp on the metric system. Now I know this is an issue because we live in the United States. We don't deal with the metric system every single day, but we kind of got to get over it because it's the way that science talks. So the units that the metric system uses are called the SI units. And here is an example of 5 of the most commonly used base SI units. We have meter, kilogram, liter, seconds, and then Celsius or Kelvin for temperature. So you're most likely familiar with all of these except for maybe that guy right there. And we'll discuss that a little bit further in the next unit of study. Okay. Oh, by the way, on that previous slide, see this little sign in the upper right-hand corner? Sorry, I mentioned this a little bit late. That means don't write this down. Okay? So if some of you wrote that down, I apologize. There, that sign tells you don't write that down. This isn't going to be tested. It's just to kind of reinforce the idea. So as we go to the next slide, you're going to see that image again right here. That means don't write any of this down. Okay? So with our SI units of measurement, we often use prefixes to show the magnitude of a particular measurement. Okay? Now this sheet that you see that I just popped up in the lower right-hand corner, I'm actually going to give you that sheet, or something similar to it. It's not going to look exactly like this. But this sheet just simply kind of explains the different types of prefixes and what they mean. So kilo, for instance, that's a multiplier for 1,000. So that means if you were to have 100 grams of material, and you said, all right, how many kilograms is that? Okay. Now you might say, whoa, well, I got to multiply that by, let's see, 1,000. But no, and actually that's not what you have to do. You don't multiply by 1,000. Okay, instead, you're going to divide by that 1,000. Okay, and I'm going to show you how to do that later in the chapter, but if you want to know 100 grams, how many kilograms is that? 0.100 kilograms. Okay, and again, I'll show you how to do this converting stuff a little bit later on. Alright, also I'm going to give you a sheet that looks like this. It's going to show you kind of the relationships of these different types of prefixes and how you can actually use standards to think of, okay, what is a liter, what is a kilogram. If we got a skyscraper, meter is a very common unit used in science. About 350 of those stacked on end to end as a skyscraper. 2-liter soda, that's pretty visible to us. Okay, a cat's about 5 kilograms. Film, which none of us use anymore because everything's digital, but the old film was usually recorded 35 millimeter film. If you're giving medicine to somebody, 20 milliliters, or as we know, 20 cc's, right? 20 centimeters cubed. Or a pair of cherries is about 5 grams. Okay, and then I also give you the actual relationships between the other prefixes on this slide. Okay, those are the other relationships. All right, but again, don't write any of this down. I will give you some sheets that give you this information. You will be able to use a sheet like this on a test. You won't have to memorize those prefixes. Those will be given for you. Okay, another big part of measuring and of unit identification is the ability to work with scientific notation. A lot of numbers that you use in chemistry class and in sciences in general are either really, really big or really, really small. Let's think of the really, really big ones. The distance between our planet and the sun. That's a big number. Or the number of stars in our galaxy. That's a big number. Or the number of atoms in a cup of water. That's a huge number. It's amazingly huge. How about small numbers? How about the mass of an atom? How about the width of a human hair? You know, these are really small numbers. So we need some type of form to be able to work with these things, and that's where scientific notation comes in. You're probably familiar with it. Just to refresh your memory, it consists of two parts. The first part is a number between 1 and 10. We'll call that n. And the second part is a power of 10. We'll call that x. And so this is kind of the general form of scientific notation, n times 10 to the x. So to give you two examples of that, let's say you had 3.1 million. If I had to write that out, it would look like this. Let's say that's the amount of money in my bank account. That's not correct, but let's just say it was. If I wanted to write that in scientific notation, it looks like this. 3.1 times 10 to the 6th, right? Okay, that's dollars. All right, scientific notation helps us shorten those really big numbers up and helps us really essentially eliminate these back zeros, these trailing zeros, okay? So the idea, go ahead and toss that decimal place in between the first two non-zero numbers. Now, if you do have a number that's smaller than 0, so let's just pick a number here. When you write that into scientific notation, you're going to start out the same way you would with the big number, except when you go to the exponent now, you're going to toss a negative sign in front of the exponent. And how did I get the number 4? Well, it's just simply figuring out how many times you got to swoop over the decimal place so that it lands in between the two non-zero numbers. 1, 2, 3, 4. There it is, and that's where my 4 comes from. All right, there's scientific notation. Moving on. In our last activity, when we did the graduated cylinders, milliliters, centimeters cubed, we actually had some awesome results. We had correlations of like 0.999, and that's spectacular. So we had some people doing some really, really good investigating. But even at that, we still have error. And a lot of that error comes from the measuring tools that we're using. Every single measuring tool in the entire world, no matter how accurate it is, how precise it is, has some degree of uncertainty. Okay? And when we're doing a particular lab, we want to let the reader know when they're reading our results how accurate our measuring tool was. This is where the things called significant figures come into play. Significant figures are defined as the known digits from a measurement tool, including one more estimated digit. And we're going to have two examples of this. The first one on the left here, I've got a bar, the black bar that you see right here. Okay, and we're measuring that. We just want to measure the length of that bar. It's pretty easy. All right, now if we take our little ruler here, it's not a very accurate ruler, but we take our ruler and we try to find that point. Well, we know for sure that it's 4, right? Let's say we're measuring in centimeters. We know that it's 4. We know that it's less than 5. So this is the known digit of our measurement. And sig figs tell us that we can include one estimated digit. So we can actually go one digit further. Well, it doesn't look like it's halfway between 4 and 5. It's less than halfway. I'd say it's a little bit under 4.4, so there's 4.3. So does that mean you and I will both have the same exact readings for the measurements? No. We should be in the ballpark. I don't think anybody's going to write 4.8. But somebody certainly could have said 4.2. Somebody could have said 4.4. That's where some of the uncertainty in measurement comes in. Let's look at a better measuring tool. All right, this time we certainly know it's again between 1 and 2. So we're looking at our arrow right here. We want to know what that points to. We know it's between 1 and 2, but we can actually go a little bit deeper. If we count all these little tick marks, we can see that the arrow falls after the 9th tick mark. It falls before the 10th tick mark, or before the 2's place. So we can go ahead and estimate one more digit. I say it falls right between 9 and the 2 place. So I go 1.95 centimeters. So this tool right here is actually a more accurate tool. It's giving us more significant figures. Okay? So that's how we report significant figures if we are the one doing the measuring. But what if we're not the one doing the measuring? What if we're the one that's reading the results from somebody else's lab? So how will you know how precise the measurements are? Well, you have to be able to track significant figures, and there are some rules that we have to follow to figure out what numbers are significant and what numbers are essentially estimated. And there's 4 main rules. Rule number 1, non-zero numbers are always significant. So if I have the following number, let's say 1,324, and I would ask somebody, how many of those numbers are significant? You'd say all 4 of them are. That's 4 significant figures. Every single one of those numbers has been measured. It's a measured value, so you report those numbers in your lab work. Second of all, captive zeros are significant. So if you have a number that has zeros captivated between 2 non-zero numbers, like 1,002, you have 4 significant figures again. Okay, 4 significant figures. These are measured values. If you have a number like 1.006, 4 significant figures. They're captive between 2 non-zero numbers. If you have a number like 1.00003, 1, 2, 3, 4, 5, 6, 6 significant figures. Okay, those are captive zeros. So the zeros are measured. They're said to be measured. Trailing zeros are significant if there's a decimal place in the number. Okay, so I'm going to give you 2 examples here. Here we go, 1.030. This is what we call a trailing zero. If there's a decimal place in the number, which there seems to be, this trailing zero is significant. So we would say that there's 4 sig figs. On the other hand, if there's not a decimal place in the number, so let's look at the number 100, that's bad, 1,330. This zero that you see right here is what we call a placeholder. So that's not a significant figure. And in this case, we've only got 3 sig figs. Okay. And lastly, the last type of zero are leading zeros. Leading zeros are never significant. They are just simply placeholders that allow us to get to the measurement. Here's where we see leading zeros. For really small numbers, we see leading zeros. 0.00015. In this number, there are only 2 sig figs, just those 2. These are what we call leading zeros. They are not significant. Now, if I put a 1 in front and have 10.00015, then every number there is significant. And I no longer have 2. I have 2, 4, 6, 7 sig figs. Okay? All right. But if they're leaders, they're not significant. There are a couple tricky cases for this. Let's say you get a number of 710. And that number is 710. You've measured it to be 710. And you want that zero to be significant. There's a way that we can kind of cheat the system. We can write 710 as follows. 710 with a decimal place after it. Remember our rules. Trailing zeros are significant if there's a decimal place. And you might say, well, why don't I just put a 0 after that? Because we're not certain about this 0. We can't do that. Okay? We can put a decimal place there. So if you see a number written like this with a decimal place after the 0, 3 sig figs. Okay? One more case, one more tricky case. Let's say you have a large number. Okay? Let's say the number is 3,200,000. And you are sure of that number down to, let's say down to this 0 right there. Whoops. Try that again. This 0 right there. Okay? Well, you can't just lop off the other 3 zeros and say, well, the number is 3,200. Boom. No way. This number is nowhere near this number. Okay, I'd rather have this much money than this much money. All right, so how do we get around this? Well, this is where we're actually going to use scientific notation. If we want to go down to that number as a significant number, we can write this as 3.200 times 10 to the 6th. The rule is every number to the left of the multiplication sign in scientific notation is a significant figure. Okay? All right, last slide now. Now there are going to be times when we're going to have to come up with a final conclusive answer, and that answer can only be as certain as your least certain measurement. Let's take a look at an example here. Let's say we do a little bit of math. We're finding the volume of a cube, and we find one side is 32.0 centimeters, the other side 0.2223 centimeters, and the third side 10 centimeters. We know how to find the volume. We multiply all those three together, and we get an answer. Now, unfortunately, we have one measurement that's very, very inaccurate. This guy right there. Is that 10.3? Is it 10.4? Is it 10.1? We don't know. So our final answer can only have as many sig figs as our least accurate or least certain number. Well, this number right here only has one sig fig. So our final answer can only have one sig fig. And so we have to report our final answer as 70 centimeters cubed. It doesn't matter how hard you work at getting the most certain number. That rule carries out for division as well, same thing. So what about addition and subtraction? Okay, so for addition and subtraction, now instead of looking at all of the numbers in the particular problem, all you have to do is take a look at how many digits are to the right of the decimal place. For this number right here, you have one digit to the right of the decimal place. For this number here, you have two digits to the right of the decimal place. That means your final answer can only have one digit to the right of the decimal place when you do the subtraction. So 3.7 mils is going to be my final answer. This rule is the same for addition as well. All right, there we go. That's 1.3.